supernovae, but just to measure many more of them. Density of mass, the bluer is the lower density. So we're using this technique to again map out the dark matter of these systems. The other thing I mentioned, we're also using this survey to find supernovae. And so here's one example. If I take, so again, this is that picture of the Fornax cluster. I'll zoom in on one particular CCD and blow it up, and then focus on the lower portion of that CCD and blow it up, focus it on this one particular galaxy. And then if I flip back and forth between two pictures of that galaxy taken a few weeks apart, then you see something has appeared, and that's a new supernova that we discovered in October of 2013. So we've now discovered well over 1,000 of these supernovae. Supernovae can be hard to see. If you're sitting up front, you can probably see it. If you're sitting far away, it's harder to see, but fortunately they come with these green arrows. That makes it much easier to find. Okay, so this is actually the geometry of our survey, the footprint of the survey on the sky. So this is a picture of the sky in celestial coordinates, the coordinate system defined by the rotating Earth. The plane of our galaxy, of the stars rotating our galaxy, is this dotted line. We want to stay away from that, because if we have to look through the plane of our galaxy, a lot of the light's going to be absorbed and scattered by gas and dust in our galaxy. So we want to look outside of the plane, this region of the sky. And then we also want to see what we can see overhead from Chile at night. And that's this, so we focus on this kind of purplish, reddish, pinkish region here. So this is a region that covers about 1/8 of the total sky. And what we're doing over the course of these 5 years is just taking many snapshots through each of those 5 filters over this whole area of sky, and making deeper and deeper maps. The little yellow regions, those are where the supernova fields, those are the ones that we come back and we point in those directions roughly once a week to discover supernovae and measure their brightnesses. And then the data that we've mostly analyzed so far is in this green patch. This is data we took before we actually started the survey, when we were kind of testing things out. We called that science verification. So this is now a map of the galaxies, of a couple of million galaxies from that greenish area over in the lower right. And again, you see this kind of filamentary structure of the galaxy distribution, showing you the large-scale cosmic web. Again, this region of the sky is only 3% of the area that we will eventually cover. This is actually a map of the dark matter in that same region of the sky using this weak gravitational lensing technique. And there's a nice correlation between where the dark matter is and where the galaxies are. That's not surprising. We think galaxies in the cosmic web mostly trace out where the dark matter is. But we can now actually make maps of it using this lensing technique. This is now a more recent map that we've made. This covers about 1,000 square degrees. This is from the first of our 5 seasons, and this is the data that we're now analyzing. So this is again showing you the distribution of a few tens of millions of galaxies over the sky. You see this frothy filamentary structure of the cosmic web. And compare that to the region we've already analyzed. It's a much larger data set that we now have to play with. One of the things we've done is, in addition to using this data to probe dark energy, we can also use it to probe dark matter. And so here's a map showing you, again, that pinkish footprint on the sky, now superimposed on a picture of the southern sky from the telescope. And the little red dots are nearby galaxies that we discovered just last year. These are galaxies that are in galaxies that are ultra faint. Some of them may contain only 1,000 stars or so, compared to the billions of stars in a typical galaxy. And these satellites of our own Milky Way galaxy, much like the large and small Magellanic Clouds are satellites of our Milky Way. But these are much, much smaller, much fainter, and so we simply haven't been able to discover them until we've made this map. So we discovered 17 of these nearby dwarf galaxies just last year. And as I said, these little faint galaxies have the advantage that they're relatively nearby to us, to the Milky Way, and they're very rich in dark matter. They contain very few stars, mostly dark matter. And so we're searching in these dwarf galaxies to try to see the signal of that annihilation of weakly interacting massive particles. So this is now a gamma ray image from the Fermi Gamma Ray satellite of one of those dwarf galaxies that we discovered last year. We don't see any significant excess of gamma rays coming from that galaxy, so that allows us to put constraints on the nature of dark matter. And finally, a couple of other sort of fun things that have come out of this, nothing to do with dark energy or dark matter, but when you make a large map of the sky, it turns out to be useful for a variety of other things that we hadn't even thought of when we designed and started the survey. Namely, we can use this, we think, to understand more about the nature of our own solar system, the very nearby universe. So in the upper left is showing you the inner solar system, the sun surrounded by the inner planets, then the asteroids, and then Jupiter. In the upper right, we're zooming out to see the outer solar system, including Uranus, Neptune, and Pluto, former planet, which we now realize is just one of a very large number of objects that we call Kuiper Belt objects. And in the lower right, we have a zoom out even further, so the solar system is now all contained in here. And in red is the orbit of an interesting planet called Sedna that was discovered a number of years ago. And Sedna, we think, is sort of has two orbits, and then we go even further, we get to where we think there's this vast cloud of stuff called the Oort cloud. And so it turns out that there's actually many hundreds of thousands, not only of inner solar system asteroids, but these Kuiper Belt objects, and more generally what we call trans-Neptunian objects, things outside the orbit of Neptune. And so here is a plot on the sky of the known trans-Neptunian objects superimposed on the sky. And so basically this curve is just tracing out the plane of orbits of planets in the solar system around the sun. But you can see that a number of these things should be within the footprint of our survey, and we should be able to detect them because they move around over time within our survey. So if we take pictures over the course of 5 years over our footprint, we'll see some of these objects move around, and we'll be able to trace out these trans-Neptunian objects and learn more about the solar system. And in particular, these supernova fields are very good for that because we observe them roughly once a week. And so over the last few years, we've detected a number of these new trans-Neptunian objects by looking for things that move over the course of weeks or months through these fields over time. So this is a listing of all the new trans-Neptunian objects we have discovered as of last year. There was a lot of excitement in the astronomy community a month or two ago because two astronomers postulated the existence of a new planet. You've probably heard about it, called Planet 9. This is a planet that would have about 10 times the mass of the Earth, and it's postulated because of the regularity of the orbits of a number of these trans-Neptunian objects, including a couple that were found with our camera. And we've been quite excited about this because if Planet 9 truly exists, we think there's a good chance, this is the likely orbit, that the orbit of this object is constrained by actually studies of the Cassini satellite orbiting around Saturn. If there was any additional mass out there, it would show up as a perturbation of that orbit. And so the most likely range of orbit for this Planet 9 directly crosses our survey footprint. So we have people in our team now trying to use our data to see if we can see any trace of this possible hypothetical new one. And finally, as Andre mentioned, there was a lot of excitement last month with the announcement of the discovery of gravitational waves. This is a sort of warping of space-time that was predicted by Einstein's theory of relativity 100 years ago. And basically, what they discovered was the signal, the chirp, due to two black holes, each 30 times the mass of the Sun, orbiting each other and eventually spiraling in and merging. And that's a very violent event from the point of view of space-time. It sends out these ripples of space-time, which were observed by the LIGO experiment using these two huge detectors, one in Washington State, the other in Louisiana. This is quite exciting, and LIGO is going to turn on again later this year. And we realized that LIGO was going to be turning on last year, and so we formed a project using our camera and our survey, such that when LIGO said gee, we think we maybe have seen something, we would go and point our camera in the direction of the sky where they thought it was coming from, and see if we could see an optical light counterpart to these gravity waves. Now the problem is that with only two detectors, one in Washington and one in Louisiana, they couldn't determine very precisely where on the sky these gravity waves were coming from. To triangulate, to really determine the direction precisely, you need 3 points of a triangle. They only had 2, and so they had a rather large uncertainty in where on the sky this was. And so within a couple of days, we pointed our camera at the most likely region of sky where LIGO said they thought they saw this event, and we were searching for an optical counterpart. We didn't see anything. That's not too surprising, because if they're black poles merging together, it's unlikely that you would form something that would give off an optical type. However, in the future, LIGO will be sensitive not only to black holes merging, but also to neutron stars merging. And we think there's a good chance that when neutron stars collide together, they would give off an optical type. So we will hopefully continue this program in the future. It kind of piggybacks on the survey that we're carrying out and synergizes with it in a nice way. And so our hope is that in the next year, perhaps, we may be able to discover optical counterparts for gravitational wave events for the first time. This is a picture of the Orion Nebula. This was taken with the Dark Energy camera. It has nothing to do with cosmology, but I thought it was a nice picture. And this also has nothing to do with cosmology. This is a comet. So when we're pointing, a computer tells us where to point the camera on any given time at any given night. Our computer doesn't know about comets, and so there just happened to be this quite bright comet Lovejoy, that was passing through while we took the picture, and so it makes a nice, pretty picture. All right, to summarize, the universe is about 13.8 billion years old. It's about 95% dark, 25% dark matter, which holds galaxies and clusters together. There's going to be a quiz at the end. About 70% dark energy. It's filled with billions